Alright, so here we need to do some work finding matrices for linear transformations. And I'm going to do this using a little example. So I've got a derivative that maps polynomials of degree 3 into polynomials of degree 2, and I want to find a matrix for this derivative. So my thought here, the thing I'm going to need to do first is I'm going to need to pick some bases for P3 and P2. I'm going to pick these to be easy for me to deal with. So my thought is that a third degree polynomial basically looks like a plus bx plus cx squared plus dx cubed. And my thought about a second degree polynomial is that they look like a plus bx plus cx squared. And I realize I got these backwards from the quadratic formula, but it doesn't really matter. So what this means to me is that I can make a basis here. So looking at this guy, I'm thinking that means that a basis for P3 is given by the vectors. I'm going to describe these as vectors, and those vectors are going to be 1, x, x squared, and x cubed. And up here I'm thinking here's a basis for P2, which is 1 and x squared. There's nothing particularly special about these, but these are going to make my life a little easier. So what I'm thinking, all right, what does the derivative do? So I'm going to take the derivative, I'm going to apply, right, that to a function in P3, so an a plus bx plus cx squared plus dx cubed. Out of this, I'm going to get another vector. This is going to be a two-dimensional, or a second degree polynomial. So I'm going to get b plus 2cx plus 3dx squared. And then I'm going to go ahead and I'm going to write down a matrix. So the way I'm going to write down my matrix here is I'm going to think to myself, all right, if I apply this to a vector in this P3 space, which to me is going to look like an A, B, C, and D. So this A is on the 1 coordinate, this B is on the x coordinate, the C is the x squared coordinate, and the D is the x cubed coordinate, right? I need to see out of this that I ought to get this new vector, and my new vector here ought to be B and 2C and 3D. And again, those are in the 1's space for the B, the x space for the 2C, and the x squared space for the 3D, right? Now, I need to make this kind of work, so I'm going to say, all right, if I did derivative to the first basis vector, 1, I would get 0 out of it in every space. So I'm going to get a whole bunch of zeros here. I should probably check sizes, because I think I just screwed up sizes. So this takes a 4-dimensional input space and turns it into a 3-dimensional output space. So my matrix here should be 3 by 4. So I put in one too many zeros just there. So I got my zeros. That's my derivative of 1. The derivative of x is 1 and no x's and no x squareds. The derivative of x squared is no constants, twice whatever I have here, so I get a 2 here, and then I get no x cubes. So that's me differentiating 2x, right? Or sorry, x squared and getting 2x. Then my next one's going to be me differentiating x cubed, and I'm going to get none of these, and a 3 here. So this is my matrix for the derivative. So I should probably fix my sizing there a little bit. Okay, so that's my 3 by 4 matrix that describes the derivative here. Okay. Now, let's move on to a slightly different thing. So let's find a matrix for the antiderivative from P2 to P3. Again, I'm going to use those same bases, right? So I'm going to think to myself, all right, what happens when I integrate a plus bx plus cx squared dx? Well, out of that I get an ax plus a b over 2x squared plus a c over 3x cubed, right? So when I'm constructing my matrix, I'm going to be taking a vector a, b, c, and out of this I should be getting a four-dimensional vector, and my four-dimensional vector has a 0 in the first space, an a in the second space, a b over 2 in the third, and a c over 3 in the fourth. So I need to think about that over here. So my matrix here ought to be, well, it's 4 rows by 3 columns, right? Because I'm going from a 3-dimensional space to a 4-dimensional space. And then in this first in this first column, I'm going to get what I would get by integrating 1, which is going to be 0 and 1 in the x spot, 0 in the x spot, 0 in the x squared spot. In this next one, I'm going to be getting the thing that I would get by integrating x, right? So that's going to be a 0 in the middle spot, a 0 in the x spot, a 1/2 in the x squared spot, and a 0 in the x cubed spot. And same thing for the integrating x squared component. So I'm going to get a 0, 0, 0, and a 1/3 here. Okay, now, trick is, we should probably multiply these together and kind of see what happens. So I want you to make a guess. So I'm going to call this matrix here my antiderivative matrix. I'm going to call A for anti. And I'm going to call this matrix here D for derivative. And then I want you to think to yourself, what am I expecting to have happen for AD and DA? So this one's differentiate first, then anti-differentiate. That may be, well, I want you to think for a second. This one's anti-differentiate first and then differentiate. I want you to think about which one of those ought to give us the identity and which one ought to be a little different than the identity. So take a second, think about this, pause the video. Think about this for a second. Alright, I'm hoping you paused the video and you're back. So I've got my D and A matrix entered here. And then I'm thinking, alright, I feel like if I anti-differentiate, I'll get I'll have that up to a constant bullshit, but then when I differentiate, it'll go away anyway. So my call is that DA ought to be I, and that AD, if I differentiate first and then anti-differentiate, I should run into some problems with constants or something. So I think that one's maybe not going to work. Another way to think about this is to think, all right, D takes P3 to P2, and A takes P2 to P3. Right, so AD does P3 to P2 back to P3. That should be a problem. The fact that I smashed a big space into a small space and then back ought not work. Down here, A takes P2 to P3 and then takes that back to P2. That one could maybe work out for me. So let's go grab our little linear algebra thingamajig and try it. So AD gives me a square matrix that has identity columns in it, but it doesn't have a 1 in that first column. That indeed isn't the identity matrix, basically because I don't know what to do with the constants, right? If I do the other way, if I do DA, I do indeed get the identity matrix. So this is what's called a pseudo-inverse, right? This is one of these things that we said, yeah, inverses in linear algebra are supposed to be two-sided. here's a case where I have a one-sided inverse. We call that thing a pseudo-inverse here. Hope this has been helpful. Thanks for watching. Catch you guys later.